Hello, this is Math 4. This is an intro to statistical reasoning. Statistical reasoning is used when you can't get exact results. You're using data pulled from some sort of an experiment, and in order to do that, you've got to have an experiment that is pretty well designed. You may be familiar with a lot of this from science class. This is on page 77, problem number 2. We are assuming that you have done problem number 1 on page 76. But we're going to reference that problem, so if you haven't seen that one, don't worry. Problem number 2 on page 77 talks about, in a typical experiment, 2 or more treatments are randomly assigned to an available group of people, or animals, or plants, or objects, or whatever else. One of the key words here, by the way, is randomly. These objects in the available group of whatever we're working with are called subjects. The purpose of an experiment is to establish cause and effect. What that means is, does one treatment cause a different response than the other treatment? A well-designed experiment must have 3 different characteristics, and it has to have all 3, or it is not a well-designed experiment. There has to be randomness in it. The subjects are randomly assigned to the treatments. A sufficient number of subjects. Subjects will vary in their responses even when they are treated alike, whether we're talking about seeds or people or any kind of situation. If there are not enough subjects, this variability within each treatment may obscure any difference between the effects of the treatments. What that means is simply, you can't tell if the experiment told you anything if you do not have a sufficient number of subjects. Deciding on how many subjects are sufficient is one of the more difficult tasks that statisticians do. Is 10 enough? 20? Or do you need 200 or even 1,000 in order to make a good decision? Comparison group or control group. In science, we usually call this the control group. Either the group that gets the treatment is compared to a group that gets no treatment, or 2 groups that get different treatments are compared. The group that gets no treatment is called the control group. That's very important so that you can see if there's a different effect when you apply the treatment to your subjects. On page 77, problem number 2, part A asks us which characteristics of a well-designed experiment were missing in problem 1 in the mung bean seed study of the 3 people. We're going to take them one at a time. Here we're referring to Carlos's experiment. For his experiment, Carlos just zapped 10 mung bean seeds and saw that 8 sprouted. The problem with Carlos's experiment here is that he did not have any kind of control group. He didn't leave some seeds unzapped, and he just watched what happened to the 10 that he zapped. There's no way to tell what effect the treatment had on that. The treatment is zapping them, and the response is whether they sprouted. Carlos simply couldn't tell if his experiment had an effect because he had no control group. Therefore, not a well-designed experiment. Mia, on the other hand, Mia took 20 mung bean seeds and picked out 10 and left 10. The problem was, so she had a 10 seed, or half of them were in the control group. The problem was that she didn't randomly assign them. She looked at just the healthy beans and zapped them. Instead of randomly assigning them, she just picked the ones that she wanted. There's no way to tell if the treatment had an effect or if it was because she picked the healthier looking beans. Julia, in her experiment, she took 4 mung bean seeds and selected 2 at random. So good, she selected 2 at random. So she had a control group and a group that she applied the treatment to, but the problem was, of course, she only looked at 4 mung bean seeds. and that's simply not enough to tell if the treatment had an effect. You need to have more. How many more? Well, that's a good question, and in this case, we don't have a solid answer for that. We'd need to know a little bit more about it. In her experiment, though, she did 2 of the 3 things right. That's just not good enough, though. She has to have all 3 for them to be a well-designed experiment. In Part C, we're talking about what can go wrong if the treatments are not assigned randomly. Randomness is one of the big parts about this, one of the things that can really mess up an experiment, even if you do the other things correctly. Notice, please, that we skipped Part B. We haven't done the penny stacking yet. So, what can go wrong if the treatments are not assigned randomly? Well, you just can't tell if you've picked things based on some other characteristic that is going to make your experiment kind of invalid. For example, in one of the previous slides, the student picked only the healthy-looking seeds, so there's no way to tell if her experiment, if more sprouted because the seeds looked healthier, or if it was because they were zapped in the microwave. Now, that's a very easy example to understand. Understanding why randomization is important in other situations might not be so obvious. In that one, she picked the healthier-looking seeds, so it obviously wasn't random. But if you just pick a pile of something and you put half to one side and half to the other, that's not really random. There could be some characteristic that you're not aware of. So you would want to randomly assign things to groups, whether the treatment group or the control group or the 2 different treatments. So knowing that your experiment is going to be valid depends very much on the idea of introducing some sort of random variable into picking them. The random variable could be flipping a coin, rolling dice, or using a table of pre-generated random numbers. Computers have a problem with that because they don't truly use random numbers, but for most things that we do, computer-generated random numbers are perfectly okay. We are now done with this problem, and that should explain the 3 characteristics of a well-designed experiment.